Welcome back to the channel, everyone. We're excited to have a returning guest today, Asher Brandt, also known as Quantum Psychedelics. Asher is an assistant professor of biochemistry at the University of St. Joseph, where he specializes in researching the pharmacology of psychedelics. If you haven't yet, we've done multiple videos with Asher in the past, so definitely check those videos out. A couple of weeks ago, I saw a really cool MD simulation of DMT on your social channels, and I was like, oh my gosh, we have to make a video about this. So reached out, and here we are about to make a video. So Asher, if you could just tell us a little bit about the structure, the papers that you reviewed, also the MD simulation, and then we can jump into VR and check it out.
Yeah, I saw this structure come out in 2025. It's led by Gumper, who is a PI at the University of Chapel Hill, also where Brian Roth's on this paper, as well as David Nichols, who a lot of you probably are aware of. So I saw this great structure, and it has actually 7 or so compounds found to serotonin too. So it's loaded with really cool crystal structures, including a psilocin. It has a DMT crystal structure. It has a mescaline crystal structure, which is incredibly novel. It's got a few others, but I thought the DMT one was the coolest of the bunch, just because of people, have mystical experiences using DMT, we'll say. So I saw this crystal structure, and I thought, I didn't see MD in the paper, so I wanted to run an MD simulation. So I hopped onto Maestro and ran an MD simulation. The simulation itself is 100 nanoseconds, and we did 50 frames, and basically nothing earth-shattering we see in the simulation. What you really see is that you see the aspartic acid 155 salt bridge really stabilize the ligand inside the protein, as well as the serine 242 hydrogen bond, and some of the pi interactions with phenylalanine, phenylalanine 39, and some of the other aromatic amino acid residues. But to give a little backstory on all this, most people had been sort of wondering, because for the longest time, Brian Roth's group just had a serotonin 2A crystal structure. Back in, I think, 2022, that first paper came out with LSD bound, and that was super cool. So what I was curious is, well, do all indolamines bind this way, where you have the serine 242 hydrogen bond and aspartic acid 155 salt bridge? Of course, you're always going to have the aspartic acid 155 salt bridge, but does it stay bound to hydrogen bond serine 242, or does the conformation flip? And that was kind of flipped on its head maybe 2 years ago. There was a group in China that came out with a crystal structure paper, and it had psilocin bound. And the ligand inside the binding site was actually in a flipped conformation. You had the aspartic acid 155 salt bridge, but you didn't have the serine 242 hydrogen bond. It was in a different conformation in that way. It was kind of flipped. And I thought that was interesting, but I thought it was strange. A lot of people would expect that you would see this conformation where you'd have serine 242 hydrogen bond, aspartic acid 155, and that's just how all indolamines are going to bind. So it didn't have that conformation. So then in 2025, Gumper comes out with this paper, and it has those conformations. And I thought that was really cool. It kind of validated that probably is the more stable conformation inside the binding site. But of course, we have to realize that crystal structures are snapshots. They're static structures. They're not accounting for MD or moving within a binding pocket. They're negating time, right? Which is what MD solves for us. So yeah, I saw these cool crystal structures, ran MD, and it kind of really stays really snugly inside the binding pocket.
Well, thanks so much for that context. We're going to go ahead and jump into VR together. Just as a heads up, Steve will be the one guiding us through along with Asher inside of VR. So we'll see you in VR.
The paper has 7 psychedelics bound to the serotonin 2A receptor, including this is psilocin inside the binding pocket. And I thought this was really interesting because for a long time back in 2022, the serotonin 2A LSD crystal structure paper was published. And what's interesting about all this is that this binding pose is actually very similar to LSD's binding pose inside the binding pocket, which makes sense because this is also an indole structure similar to LSD.
Nice. And so you run MD on this, so molecular dynamics, so you could actually see it move around within the binding pocket.
So what I think is important to talk about with specifically serotonin 2A and a lot of GPCRs is they all have this aspartic acid residue right here. Not all of them. Cannabinoid receptors don't, but dopamine, serotonin receptors do. A lot of other GPCRs have this conserved aspartic acid. And basically, there's an amine group right here, and it's a positively charged NH NH plus. In this case, it's NH3 plus, and it forms a salt bridge between the aspartate residue and the amine. And if you mutate that residue to something that can't salt bridge, you actually destroy the activity of the drug. So what you'll notice is if you'll really look throughout the whole simulation, you're not going to lose that salt bridge interaction. It doesn't ever go away. That's the most stable interaction holding the drug in the binding pocket.
Let's go ahead and just kind of make that connection. So,
Sure.
Which one should we do? Nitrogen, oxygen, or should
We can do. I mean, technically, technically, if you want to get right, it's between it's N plus and the O minus. So you can do it between nitrogen and oxygen is the right way to do it.
Yeah. Ignore the hydrogen.
It can be either or. Yeah.
Well, I guess was kind of cool is now we could go through the frames and really see what you're saying, that that distance doesn't really deviate too much, and
No.
that the rest might be moving around a bit within the pocket, but that's a really stable connection to that salt bridge.
There is another one that's really constant in this. If you look at the indole hydrogen here, if we displayed all the hydrogens, there's a hydrogen bond between the indole hydrogen and serine 242. I don't know if we want to try and pull that up or not. If it makes it more complicated, we don't have to.
Yeah, sure. We could at least do a little measurement. So actually, let me double check, make sure it's the serine 242. Serine 242. Yeah, that's it. Highlighted right there. So let's take our little measurement tool and go ahead and do that. Yeah, I mean, the hydrogens, we can imagine.
Yeah, whatever. We don't need it. But what's interesting, if you think about it, Steve, if you also play the MD simulation as you were before, that also doesn't change too much. It really gets held inside the binding pocket. There's a few other residues. There's a pi-pi interaction, but we can just look at the hydrogen bond and the salt bridge. It doesn't deviate a lot in the whole simulation. It stays
it
pretty
seems
constant.
like this whole pocket has a lot of potential for like pi-pi stacking, especially with these two residues. What are those?
That is a... What is that? That's the phenylalanine.
Phenylalanine
3,4.
And the tryptophan 336.
Yeah, that's right.
And even this one, what is this? Another phenylalanine 339.
339.
340. Okay, so they're like sequential. Two phenylalanines in a row.
They do pi stack, but we're not. I don't think we're able to imagine the pi. That's okay though.
Yeah,
that's fine.
Yeah, I mean, maybe
it does
we could
pi
go
stack.
through the frames and just see if there's a frame that kind of shows that better. Of course we could turn on the chemical interactions and stuff too.
Well, I think having it like this actually is pretty nice. You can see the hydrogen bond, you can see the salt bridge. Those don't deviate too much, but the really stable thing holding in place is that salt bridge. That's not going to deviate a whole lot.
Yeah. So in terms of like novel psychedelics, like you mentioned Brian Roth's paper, would you say it's pretty common to try to keep these two like anchor points the same, and then kind of mess around with this part of the ligand in terms of trying to create something novel?
It's a really great question. You don't have to is the answer. If you want to make a tryptamine psychedelic, I'd say this is the binding pose between tryptamine psychedelics. So if you think about like DMT, psilocin, 4-ACO-DMT, 4-HO-MET, all of those analogs of tryptamine psychedelics, they all kind of adopted this pose. But there's also phenethylamines. Phenethylamines don't have this pose, and that showed also in this paper. They have a mescaline-bound crystal structure in this paper. Those do have different conformations than these, but they all have the salt bridge. You need the salt bridge. You can't have a psychedelic without the salt bridge.
And what about picking up other interactions? Like, what is this? Aspartic
ASN. Yeah, this actually, you actually pick this up with the 4-HO analog psychedelics. You pick up a hydrogen bond here. So like 4-ACO-DMT, 4-HO-MET, these actually pick up the hydrogen bond here. Those are what's unique about those.
It seems like, if we had a, I don't know, extra little hydrogen bond receptor, then, we built out, you might be able to pick something up there.
Yeah, exactly you could imagine like psilocin does. It has an OH group and like 4-ACO-DMT and 4-HO-MET, and then 5-methoxy-DMT. these do have substitutions at positions around the ring where you can form hydrogen bonds here. And that's what's, I'm not going to say unique about those psychedelics, but you can pick them up totally on that aromatic ring for sure. So what's also unique about this structure is that if you'll notice a lot of, well, all GPCRs, this one was crystallized with just with just DMT and the no G protein. But what's cool about this paper is they have with and without the G protein. And you actually get a little bit better resolution when you do without the G protein. But that's a nuanced thing, I'd say.
What I'm noticing with this, I was like, sometimes it's close enough where it would probably, be good to form a hydrogen bond, and then like other frames, it got up to like 8 angstrom away, and so it's really moving within that pocket a lot in this part of the structure. Obviously, that hydrogen bond you mentioned and that salt bridge, those are staying pretty stable, and obviously we don't have a connection. Oh, that was a good one. So go back. Yeah, 8 angstrom away. This is an interesting pose right here because we conserve the distance, 3.7, 3.5 angstrom. Those are all pretty close for interactions. But yeah, if we did have that other type, like this frame probably wouldn't exist because it'd be pulling a bit closer to that. So
that's a good point. You can use sort of those analogs to pull closer to this aspargine, is what you're saying. Yeah, definitely.
Yeah, but then I guess it might not move around the pocket as much, and I guess trying to understand these GPCRs, like, is the way that it kind of moves and oscillates around this pocket also affecting how these things work, or is it more the fact that it's like bound in a certain way?
From what I understand in reading, I think it's based on it's bound in a certain way rather than how it's moving inside the pocket, because it being bound in a certain way is going to help. Well, from my understanding, stabilize the G protein better, right? That's going to enable it to signal towards G protein pathway better or arrestin pathway better. So I think it's more so the pose. But I mean, it's always like, probably both, right, is the real answer to that question.
Yeah, it makes sense. Yeah, because you can imagine like when this is tugging and it's kind of pulling that, you get this part of the protein, kind of wanting to hug in and make that pocket a bit tighter. And right now it's there's no interaction there actually happening, so this part's kind of free to do its own thing over here. While of course like this part of the protein stays bound and that part stays pretty bound.
Yeah, and that also is going to affect, right, the helix, right? Because it's going to affect the shape of this helix, and it's going to, affect how it's binding to the G protein. So I think the answer to the question is great, and the answer is both. Both are factors. I think what I was going to say is, too, you imagine this, we're talking about this thing being, this interaction, we'll say, if we had a potential hydrogen bond being 8 angstroms away, yeah, too far. But so it tells us that there's not really influence of this aspargine. What's the bigger influence? Probably
in this pose,
probably
right?
the pi is what I would say.
But you have other poses where like like if we did have a donor receptor pair here, it would probably be kind of pulling and wanting to stay in a pose more like this more often. Which is actually interesting because over here it's right around 3 angstrom and right around 3 angstrom. So you would think that, if you kind of fixed all 3 of those points together, you'd have this like really tightly bound state. But with this, we're able to kind of get further and closer with a lot of the other areas, even though these 2 areas stay there because there are interactions being picked up.
I see what you're saying. Yeah, I definitely see what you're saying.
Yeah, but you're the expert. I'm just I like looking at things in VR.
Yeah, I mean. It's a good thought, but I don't know how much of that represents reality, because if you also kind of think about more like what are the highest affinity compounds towards serotonin 2A receptors? Phenethylamines. Phenethylamines have the affinity is really tight, and it also has strong activation. And phenethylamines don't really, the pose is totally different of a phenethylamine. And if you compare something like the affinity of psilocin versus phenethylamine, it's drastic. Psilocin's affinity, tryptamine affinity, is actually not that tight towards serotonin 2A. It activates it, but the affinity is not anything impressive. It's pretty typical versus like, something like an N-bomb compound. You're looking at like 1 nanomolar affinity, which is really tight affinity.
Nice. So you also kind of screened some other compounds.
Yeah.
Maybe we could look at a few of those
Yeah,
structures.
I'd love to talk about that. Yeah.
Yeah. So this is one of them. This one's pretty big.
That is a larger compound, but well, so I'll talk about sort of what I did here, what this is. So one of the things I like to do is high throughput virtual screens. What is structural information used for in protein data bank files? One of the applications that I really like is high throughput virtual screening. So you take a PDB file, you take an active site with a ligand bound, and you can run millions and millions of ligands at the active site of the protein. And I did that with this is overall I used the psilocin structure from the paper that Gumper published. And this is a screen of 15 million compounds specifically. And this was one of the hits that came up. And yeah, it's quite a big compound. But if we think about it, what's going to be the most conserved thing here? It's going to be the salt bridge with ASP135, which is right. I believe it's right. I believe that's it right here. I think that's ASP135 right there.
So this is 155.
155. Oh, that's sorry. That's right. Yeah. Sorry. ASP155. I'm saying 135. But yeah, 155. So that's going to be your most conserved residue because, that's what holds the protein in place. 3.4 angstroms. And I guarantee, I know that if you look at all the structures that we have for these novel compounds, you're going to have that interaction. This is a big ligand. You're right. This is quite large. It kind of almost... So if you think about it, Steve, if you kind of think about this structurally, this is an indole, right? And then you have your linker where you're positively charged amine. And then you've got this sort of... aromatic ring with a C triple bond end. It almost kind of reminds me of like an N-bomb-like compound.
It's pretty cool. So yeah, if you're able to see the surface, you kind of like get inside the bonding pocket a little bit.
I love it. Wow, I love it.
Yeah, I was hoping we kind of see just like how deep the space went, but it's a bit hard to figure that out. So we are the ligand.
I kind of disagree. You can figure it out. So you have if you kind of look deep in, you have this black space over here, which represents your boundary region, I think. So no, I can kind of see how it fits snugly inside the binding pocket. This looks really cool, though. I like this.
Yeah, definitely. Yeah, I like, doing some molecular spelunking. Yeah, maybe, this.
Well, and here's what's cool, Steve. If you zoom all the way out, so we're zoomed out in surface mode. There's kind of a cavity here, and you can think about that as a hole, a big cavity, and that's probably how the drug is getting inside the receptor to begin with and getting out of the receptor, right? Getting in and out.
Maybe we could actually look at a few of the other structures.
I'd love to.
So actually, it looks like you I've already aligned them pretty well.
Ooh, that's beautiful. I like that.
The
Well,
origin point.
well, I
maybe
didn't
we could just
really.
kinda, color
Yeah,
them
they're.
a bit differently.
I like how you did that alignment that came together really nice. Well, because they're all the same PDB file, and it's a static frame. They will merge together perfectly. It's a static docking frame. It's not like an MD frame or anything.
Cool.
But this looks cool.
Right.
Yeah.
Yeah, we'll just get a few different colors going for
Each ligand.
each ligand. Yeah. Okay, cool. Yeah. So these are just three. I know that you've done 9 of them, but
We don't have
you
to.
have 3 more of these compounds. So all of these were from a virtual screen that you did, where you took the structure from Brian Roth's paper, and then just ran a docking screen against a bunch of compounds, and these are kind of the top hits that you got. But they're all a bit different. I mean, I guess there's a lot of similarity. Yeah, maybe back here, a bit more overlapping areas with these aromatic rings. But over here, it seems to have the widest variance, where purple one's kind of poking over here, the yellow one's kind of poking over there, and the green's right in the middle.
I agree, but if you look, what's anchoring all these structures in a similar position, that salt bridge, right? That's what's holding them all that salt bridge is going to be the same if we kind of right here. So if, this carboxylic acid, aspartic acid 155, you have the nitrogen here, and I think in this structure in yellow, the nitrogen's here that's forming the salt bridge. So it isn't a little bit different of a conformation, but it's all being held in there.
And then we got all the 2D ligands here.
So yeah, I mean, what's cool about this is this reminds me of something like a hybrid between an N-bomb compound and a tryptamine, because it has the indole right here, and then it's also got the linker to the other side with the other aromatic group, kind of like an N-bomb compound. And this is very characteristic of 25CN-NBOH, that cyano group. And then you've got your positively charged amine there, which is going to salt bridge with ASP155.
Let's check out another. So,
Yeah,
we'll do
we
this
can just
one.
kind of cycle through.
This one's a bit different. We still got
This one's significantly different, I would say. I don't know what to say about this one. This one's significantly different. You've got the positively charged amine group. That's all I can really say. But I can't say this resembles anything that I've seen before in terms of a psychedelic compound.
Well, I mean,
This one-
this like 6-member is the first one, right? So 6
That's the first one, yeah.
And then like I guess like you kind of. I mean, it's a bit different with that oxygen hanging out. Like I see
Yeah,
the
that's
third
totally different.
one,
I don't know what to
so
say about that one.
This one's
got the
interesting, kinda got the double
it
aromatic
is.
on each side.
Yeah, double aromatic on each side, and then obviously we have the positively charged amine group, right? Let's see what else we got. Also a strange enough structure. This kind of, if you put two oxygens there, that's kind of a privileged structure like MDMA, but that's not quite the furan group there. But that's kind of a similar thing going on there. This one, there's your positively charged amine, the aromatic and a fluorine.
Yeah,
okay.
the fluorine's kind of interesting.
Well, that comes up a lot in med chem,
yeah.
yeah. It comes up, but yeah, definitely different in terms of these structures.
This one's interesting.
Yeah, this is very interesting. This hydrophobic tail at the end, right? Very hydrophobic tail. But we had a structure that also had this functional group on it before. I remember there was another one that had the same functional group on it.
And then I think this one's the last one. And we got a
Yeah.
big ring over there. That's kind of.
But similar, this group came up in three of the structures. This ring system over here.
Yeah,
but
well, I mean,
yeah,
this seems like a very common serotonin receptor ring. For that to be in the ligands.
Right. But yeah, this is very strange. This very large ring system right here.
See how many of these we could overlay together before it starts complaining at me.
Perfect. Look at that. That was a really cool, very slick overlay.
Yeah,
that's a cool visual. Yeah, that's a cool visual to look at.
It's like, hey,
like
look
that.
at all the things that are moving around this pocket. Like, you pretty much fill up this pocket in any way you could imagine.
Yeah, I mean, that's kind of the name of the game, right? Keep your salt bridge and fill this pocket any way you want to fill it, right? And it is pretty filled. It has a lot of different, it's filled in a lot of different spaces, I'd say.
Yeah, it kind of gives a good idea for like what this screen's actually doing, right? Because you have different interactions you're trying to pick up, but also it needs to kind of conform to the geometry of the pocket, because you said as a static dock within this structure.
Yeah, I mean, essentially, I'd say 56 years ago, this is a really hard problem to solve, because you have this is a very weird 3D shape, right? And you're trying to fit ligands in a very strange 3D shape. It's a very complicated Lego piece, right? In that respect.
Definitely. Yeah, 3D Legos. I'm gonna try to hide the surface. There we go.
Okay.
Yeah, let's kind of check that out from a few different angles. So yeah, this is pretty much just all the ligands overlaid.
Just thinking about the positively charged nitrogen. I think it's somewhere over here. I think it's in this area. Yeah, it's got to be. This is probably where the salt bridge is. Look at all those nitrogens. It's in this
Exactly.
general
All those
region.
nitrogens, right? You know, it's a very common motif, and then we got
Yeah.
all these oxygens over here, right?
Yeah. If you have a bunch of nitrogens there with the common motif and a bunch of oxygens, this could be where you're picking up. I mean, yeah, I could be wrong, but the hydrogen bond with ASN 343 or serine 242.
It's always nice to understand the new science coming out, and Brian Roth's paper was obviously really cool. So thanks Brian Roth and collaborators for sharing this information, and thanks Asher for showing us this MD as well as your virtual screen.
Of course, and obviously the MD wasn't run in the paper. I ran the MD, but I mean, Brian Roth's group has an instrumental amount of GPCRs now, especially psychedelics with different ligands bound. So it's been really cool to see those structures come to light and see how different psychedelics do bind to the active site of serotonin 2A. So yeah, obviously gratitude to Brian Roth's lab and Ryan Gumper now.
Okay, this is awesome. Well, yeah, thanks again, Asher.